In previous chapters, we have dealt with constant forces. These produce constant accelerations, which allow us to use our kinematic equations of motion and to calculate the work being done by a constant force. However, there are many situations that can occur in which the forces involved are not constant, but rather change in time. In fact, we can think of many examples where large forces act for a short period of time. Car collisions, hitting a tennis ball with a racket, or a baseball with a bat. The plot shows the force as a function of time for this last example. The magnitude of the force is 0 at the instant t initial just before the bat contacts the ball. During contact with the bat, the force rises to a maximum and then returns to 0 at some time t final when the ball leaves the bat. The time interval, delta t equals t final minus t initial, when the ball is in contact with the bat, is often quite short, maybe only a millisecond, but the force can be large, often thousands of newtons. For comparison, the plot also shows the average force acting on the ball during contact. To describe these time-varying forces, we will introduce two new concepts. The first is called impulse, and the second is linear momentum. We will use Newton's laws of motion to show that an important relationship exists between them. In hitting a baseball, for example, both the magnitude of the force and the time interval over which it acts on the ball are important. In fact, the impulse of a force is defined as the product of the average force and the time interval over which it acts. Like force, impulse is a vector quantity and points in the same direction as the average force. The SI unit of impulse is the Newton second. Now let's take Newton's second law and write the average acceleration in terms of the change in the velocity divided by the change in time. Notice in the numerator on the right-hand side that we have a quantity that is equal to the product of an object's mass times its velocity. This shows that the net average force on an object is related to the initial and final values of this quantity, mass times velocity. This is a new quantity that we define as the linear momentum. We represent it with a lowercase p, and it is a vector quantity that is equal to the product of an object's mass and velocity. It points in the same direction as the object's velocity vector, and it has SI units of kilograms meters per second. In terms of momentum then, Newton's second law is written as the net average force is equal to the change in momentum of the object divided by the change in time. If we multiply both sides by delta t, then we derive an expression known as the Impulse-Momentum Theorem. Notice that the left side, which is now the product of the average force times the change in time, is just the impulse we defined earlier, and the right side is the change in momentum. Therefore, the Impulse-Momentum Theorem tells us that the impulse of a force acting on an object is equal to the change in the object's momentum. In many situations, like collisions for example, it is often difficult to measure the net average force and therefore to determine the impulse directly. However, it is usually straightforward to measure an object's mass and velocity, so that its momentum just after and just before a collision can be calculated. The Impulse-Momentum Theorem allows us to gain information about the impulse indirectly by measuring the change in momentum that the impulse causes. If we also know the time interval over which the impulse occurs, then we can calculate the average force.